We have seen in the past few lessons how the series expansion for inverse tangent can help us find pi, specifically by adding an infinite number of terms, as seen in the second line. The sum converges on pi over 4. The problem with this is that the method is slow to converge. After 500 terms, we still failed to achieve 2 digits of accuracy past the decimal. Can you think of any ways we could overcome this problem? One very effective way is to make x smaller. As we've seen with other series, making x smaller than 1 really pays off in the higher order terms. That's because a small number raised to a high power tends to approach 0. As we add terms closer and closer to 0, that indicates we are converging. So how specifically do we make x smaller? Do you remember this identity from our studies in trigonometry? I've included it here for convenient reference, but if you'd like more details on where it comes from, feel free to check out those lessons. We are going to plug in the specified values for alpha and beta. Here, a over b represents a generic fraction. Plugging in those values looks like this. Notice that tangent of inverse tangent cancels out, leaving only the arguments a1 over b1 and a2 over b2. Next, we find a common denominator to add fractions, and some simplification leaves the final answer on the right-hand side. Taking the inverse tangent of the left-hand side cancels the tangent. To balance that out, I must also take the inverse tangent of the right-hand side. The final result is boxed in orange. Remember that. We are going to use it repeatedly. Consider the fractions 1/2 and 1/3. Plug those numbers into the expression we just derived. Notice it equals the inverse tangent of 1. We already know this is equal to pi over 4 from previous lessons. So it is that both 1/2 and 1/3 are less than 1. So the series expansion should converge more quickly. This is a spreadsheet of the numbers, up to 10 terms in the series expansion. Hence there are 10 rows. M represents every odd number, 1, 3, 5, 9, etc. The third column is 1/2 raised to the power m and divided by m. Of course, every other term is negative. Same thing in the fourth column, except we use 1/3. For each row, we add those terms together, as seen in the purple box. To get the total sum, we add every term in the fifth column up to that row, as seen in the orange box. In this example, the number in purple is our series expansion truncated at 3 terms, n equals 3. The sum converges on pi over 4, so to get pi we must multiply by 4, as seen in the last column. Notice our estimate gets closer and closer each time we include another term, more digits of pi in each row. I have repeated the last column here and calculated the absolute error. As we've seen before, the number of digits of accuracy can be expressed as the negative base 10 logarithm of the error. I have graphed the results. It looks like we get about 0.7 digits of accuracy with each new term we include. After 10 terms, we already have 7 digits of accuracy. That's much better performance than inverse tangent of 1. Using the same expression we derived in the beginning of the lesson, we can express pi over 4 as the sum of 2 other expressions. Both 1/2 and 1/7 are less than 1, so they should converge more rapidly in the series expansion. I have added some color coding if you care to follow along with the details. Notice the trick is to make them equal to inverse tangent of 1, which in turn is equal to pi over 4. How did I know to choose these? Well, some clever fellow a long time ago figured it out before me. Most likely he used trial and error to arrive at that. This process is virtually identical to the one we just saw, so I will not explain it again. I've included color coordination if you wish to follow along with the details. In fact, I would encourage you to make your own spreadsheet and see if your numbers match mine. This time, note that we multiply 2 times the value in the third column and subtract the value in the fourth column. Again, the total sum, boxed in purple, is equal to the values boxed in orange, all added together. Multiply the purple value by 4 to estimate pi. That is seen in the last column. The digits of accuracy are plotted here in the same way we just saw. This time it looks like we're only getting about 0.6 digits of accuracy with each additional term. Not as good as the previous one, but still much better than inverse tangent of 1. That didn't even have 2 digits after 500 terms. So indeed, our little trick has greatly sped up the rate of convergence. We'll use the expression from the beginning yet again. This time we have the result boxed in orange at the bottom of the screen. Feel free to pause the video and peruse the details on your own. I will not explain them here. And again, we'll calculate the values for each term as so. Then we'll add twice the first one to the second. Though I didn't write it explicitly here, don't forget that every other term in the series expansion is negative. That fact is reflected in the third and fourth columns. Once more, the purple box is the sum of values boxed in orange. To get pi, we multiply that by 4. Digits of accuracy are plotted here. This time we have 10 digits after 10 terms. That seems like the best one thus far. Do you think we could do any better? Of course we can. Technically, there are an infinite number of these. This particular one is a fairly well-known expression that's been around about 300 years. Again, I can't tell you how we knew that 1/5 and 1 over 239 would work out. The discovery must have been trial and error. After the fact, when this was known, it can be shown why it is true. That's what I've done on this screen using our inverse tangent identity. The value for each term can be calculated as seen here. Same idea we've seen several times by now. Notice how quickly the numbers in the fourth column reach 0. That's what I was talking about when discussing rapid convergence. If you've stuck with me this far, I'm sure you remember by now the number boxed in purple is the sum of those boxed in orange. The pattern continues for every subsequent row in the table. Lastly, the digits of accuracy are plotted here. 15 digits after 10 terms. This one seems like a winner among the 4 expressions we've seen in this lesson. Could you find better ones? I'm sure you could. Go ahead and try to find one yourself if you so desire. However, that's all the more I'm going to show for today. We'll pick up next time with some more extensions to this approach. Feel free to ask questions in the comment section below. Thanks for watching. I look forward to seeing you then.